Welcome to the Explainer. Now, odds are you're holding a smartphone right now to watch this. But hiding right there in your hand isn't just some handy gadget, it's an absolute marvel of high-level physics. We're talking about a device that literally relies on the fundamental, mind-bending rules of the universe just to switch on.
Consider this premise. Look at your phone. It can call Tokyo, take a 4K video, and navigate you across a city. None of that would work without quantum mechanics. Sounds like a pretty bold claim, right? I mean, we usually think of quantum mechanics as this abstract philosophy, something reserved for scientists in white coats working in giant underground labs. But it's actually not. It is the literal reason your everyday tech works. And in this explainer, I'm going to prove that premise to you, step by step, and absolutely no math required.
Okay, let's dive into this. Here's our roadmap for the tour. First up, the laser in your pocket. Second, the universe's heartbeat. Third, teleporting through walls. Fourth, capturing light packets. And finally, we'll talk about why the really weird stuff is next.
So, let's kick things off with Section 1, the laser in your pocket, looking at Face ID and fiber optics.
When you think of lasers, you probably picture sci-fi movies or, massive industrial cutting tools. But your phone has tiny, real lasers built right into it. If you use facial recognition to unlock your screen, or if your camera uses an autofocus feature, you're firing a tiny laser. To understand how that laser gets created, we have to look at the quantum rule of energy levels. Now, in classical physics, you think an electron could orbit a nucleus at any random distance, kind of like a satellite orbiting the Earth. But the quantum world has incredibly strict rules. Electrons can only exist on specific, fixed floors around a nucleus. It's exactly like an elevator in a building. That elevator can stop at floor 3, or it can stop at floor 2, but it simply cannot exist in the empty space between the floors. It has to skip the spaces in between. Period.
So how does this elevator rule actually give us the laser in your phone? Well, because electrons exist on these fixed floors, occasionally an electron will drop from a higher floor to a lower floor. When it makes that sudden jump down, it spits out a tiny particle of light, which we call a photon. Now imagine taking billions of these electrons and forcing them to drop to a lower floor at the exact same fraction of a second, in perfect sync. That massive synchronized release of photons creates a super-concentrated, powerful beam of light. And boom, there you have it, a laser, sitting right there in your pocket, built entirely on quantum rules.
Moving right along to Section 2, the universe's heartbeat, satellites, and atomic clocks.
Now we're going to look at the GPS that gets you from your house to that new coffee shop across town. This feature requires an incredible, almost unbelievable combination of two completely different realms of high-level physics working together. To make it work, you need Einstein's theory of relativity and quantum mechanics. The satellites providing your phone with GPS data are orbiting high above the Earth, moving incredibly fast in a zone of much weaker gravity. Because of this, their clocks literally run slightly faster than clocks down here on Earth, and that's relativity. But managing the speed and gravity is really only half the battle. To pinpoint your exact location on a map, the satellite needs to measure time with absolute, unfailing perfection. And for that, it turns to quantum mechanics.
Over 9 billion, specifically 9,192,631,770. What is this massive number? Well, inside every single GPS satellite is an atomic clock powered by cesium atoms. This number is the exact frequency, the exact number of times per second that the electrons inside a cesium atom jump between their quantum energy levels. That jump produces a tick. This isn't just some random number engineers made up, it's a fundamental quantum fact of nature. It's literally like the heartbeat of the universe itself, providing a perfectly steady rhythm.
So the absolutely crucial point is how this affects you directly. If those atomic clocks weren't using the precise, fixed nature of quantum electron jumps to measure time, the whole system would fall apart instantly. Without these quantum jumps, the GPS on your phone wouldn't just be, a little glitchy. It would drift by several kilometers every single day. You'd be told to take a left turn straight into a river instead of the highway. So yeah, quantum physics is literally what keeps you on the road.
All right, on to Section 3, teleporting through walls, exploring the processor.
Let's dive a bit deeper into the hardware, resuming deep into the brain of your phone, the main processor. This little chip is doing all the heavy lifting, right? It's running your apps, rendering your games, managing your battery. And to do that, it relies on a superpower that sounds like straight-up magic. 15 billion. That's roughly the number of tiny mathematical switches, called transistors, packed into the processor of a modern smartphone. These switches turn on and off continuously to perform the calculations that make your phone smart. Now remember,
All 15 billion of these are crammed into a physical space that's smaller than your fingernail. How is it physically possible to make switches that small and fast? The answer is quantum tunneling. Engineers actually had to look to the quantum realm to make these 15 billion transistors function. Quantum tunneling is this very strange quantum effect where an electron magically passes straight through a solid physical barrier instead of being stopped by it. It doesn't break the wall, it doesn't go around the wall, it essentially teleports from one side to the other. Crazy, right?
Let's compare classical and quantum physics just to really highlight why this matters. In the classical physics we experience every day, if you roll a ball at a solid wall and it doesn't have enough energy to smash through, it hits the wall, bounces back, and stops. Makes sense. But in the quantum world, the electron acts more like a fuzzy cloud. When it hits that exact same wall, part of that cloud can appear on the other side, and the electron literally teleports through. Engineers harness this exact teleportation effect to make the transistors turn on and off at lightning speeds. Without this quantum tunneling, those switches couldn't be this small. In fact, if we had to rely strictly on classical physics, your smartphone would have to be the size of a house, and it would be about as slow as a calculator from the 1980s. No way.
That brings us to Section 4, capturing light packets, the camera sensor.
Everyone loves their phone's camera, but very few realize that taking a photo is an interaction with the quantum world, rooted in a discovery that actually won Albert Einstein his Nobel Prize. It explains something called the photoelectric effect. This is what happens when light hits a material, like the silicon inside your phone's camera sensor, and knocks electrons loose. Einstein realized that light isn't just a continuous wave. It comes in rigid, discrete little packets called photons, and each packet either has enough energy to knock an electron loose upon impact, or it doesn't. There's absolutely no in-between. It's a strictly quantum interaction.
So how does this build into the photos you take every day? Well, it happens in 3 pretty elegant steps. First, the packets of light, the photons, enter your camera lens and hit the silicon grid of the sensor. Second, those photons knock electrons loose from the silicon. Third, the camera's hardware measures those knocked loose electrons and translates them into digital ones and zeros. So every single time you snap a selfie or record a 4K video, you aren't just taking a picture, you are literally conducting a direct, real-time quantum measurement.
Finally, Section 5, the weird stuff is next, preparing for the catastrophe. We've gone through the phone, and we've seen how deeply reliant it is on quantum mechanics. But here's the narrative twist I really want you to grasp. Lasers, atomic clocks, transistors, photoelectric sensors. You use these dozens of times a day completely effortlessly. But in the world of physics, everything we just explored is actually considered the easy, well-understood side of quantum mechanics. I know, right? These are the predictable rules we've managed to harness to build tools. But the true nature of the quantum world is far stranger than just skipping elevator floors or teleporting through microscopic walls.
The bizarre side of the quantum realm, things like particles existing in 2 places at once, spooky action at a distance, and the terrifying idea that reality itself might not exist until you actually look at it, all of that stems from a moment in history when the old rules stopped working. Back in 1900, classical physics hopelessly broke down during a problem known as the ultraviolet catastrophe. That moment of panic in the scientific community kicked off the true quantum revolution. And that incredibly strange, mind-bending history is exactly what we're going to be diving into in our next explainer.
Until then, I want to leave you with this question to chew on. What's one thing you use every day that you never thought was quantum? The next time you pick up your phone to check a map or unlock your screen, just remember the invisible, bizarre rules of the universe that are making it all happen right there in the palm of your hand. Keep wondering, keep learning, and I'll see you in the next explainer.